Started. Good afternoon, everyone, or good morning, depending on where you are. My name is Julia Matevosyan. I'm a chief engineer at Energy Systems Integration Group, and I would like to welcome you to this 2023 ESIG monthly webinar series and give you a little bit of background on ESIG. For those of you not familiar with ESIG, we're a membership-based nonprofit organization providing our members with objective information, resources, and networking opportunities in support of the energy transition. We do this through workshops, tutorials, webinars, blogs, working groups, and task force activities, and producing technical resources and materials. If you are new to ESIG and you would like and you like what you hear in these webinars, I strongly encourage you to follow up with us, and I think you'll be pleasantly surprised. ESIG membership will give you an opportunity to participate actively in all of our working groups and task forces. You can find more information about us on www.esig.energy, as well as on LinkedIn, Facebook, Twitter, and YouTube. ESIG also serves as a leadership role with Global Power System Transformation Consortium, or GPST. The mission of GPST is to bring together key actors to catalyze a rapid, clean energy transition at unprecedented scope and speed. ESIG leads Pillar 1 of 5 pillars of GPST, and Pillar 1 deals with research agenda of the system operators. More information on GPST can be found on www.globalpst.org. Okay, before we get started, I have a few logistical matters to share with you. First of all, phones will be muted for the duration of the webinar to avoid any unnecessary distraction. For the Q&A, as usual, we'll be using Slido platform. So to ask your question, please go to slido.com and enter ESIG5 as event code. The instructions are also now posted in the chat, so you can have a look there. You'll see a thumbs up button next to the questions, and that allows you to vote your favorite questions up and help us prioritize. We plan to save about 10-15 minutes for Q&A at the end, and we'll wrap up at the top of the hour. Then an email with a link will be provided once a video file has been posted. And we also plan to provide short responses to all unanswered questions after the webinar. So please don't be afraid and post your question on Slido with the code ESIG5. All right, today's topic will be on weather data inputs for power system modeling. So as you probably all know, modern power systems are becoming increasingly weather dependent. Wind, solar, hydro production, customer demand, generation, and transmission equipment outages all strongly depend on weather patterns. Consequently, accurate power system analysis requires much more detailed weather data sets than what we needed before when we were relying on fossil fuel-dominated systems with fairly predictable load patterns. Recently, over the course of this year, ESIG convened a project team to assess the limitations of existing weather data sets that are being used in power system analysis, and also outline a process of producing comprehensive weather data sets that can meet the needs of the power system. This webinar will be summarizing the key points of this report and of this work that was convened during the course of the year. So with that, I would like to introduce our today's presenter, Dr. Justin Sharp, who led this work in ESIG project team. Dr. Sharp is a principal and owner of Sharply Focused, a consultancy dedicated to bringing the atmospheric science and electric utility sectors together. And that's what made Justin perfect for leading this work at ESIG. Justin obtained his PhD in atmospheric science from the University of Washington. He has worked in the electric power system sector since 2004 and built one of the world's first 24/7 operational renewable energy forecasting and analysis teams for Iberdrola Renewables. Justin sharply focused in 2012 and has been helping clients to utilize weather and climate intelligence with a view to enabling and optimizing the energy transition. This time, I decided not to follow Charlie's tradition of finding common acquaintances between Justin and myself on LinkedIn. This is because we've met with Justin at one of the, I think that time, UVIG workshops many years ago. And I think we know a lot of people in common in this industry. I think Justin is uniquely placed at the cross-section of meteorology and deep understanding of power system needs. And honestly, I haven't seen anyone being more passionate about this topic than Justin is. So with that, a short reminder once again to use Slido for your questions. And without any further ado, Justin, you're up next.
Thank you very much for that introduction, Julia. Let me just make sure you can hear me.
Yes, I can hear you. I can see your slides too.
And I'm honored to hear you say that you find me passionate about this topic, because I certainly am. The presentation is entitled Mind the Gaps, Weather Data Inputs for Power System Modeling. I'll start going through because I think Julia's really introduced the topic very nicely. I do want to bring your attention to the quote at the bottom of my title screen. I've used this many times. I know a lot of folks are probably tired of it, but I think it's great. Your assumptions are your windows on the world. Scrub them off every once in a while, or the light won't come in. And I think that's particularly relevant to this topic. And so have that in mind as we go.
Justin, I think you accidentally maybe muted yourself. There you go.
Am I back?
Yep.
Great. Okay. So some quick acknowledgements and a disclaimer.
And Justin, you're not sharing your screen anymore.
No. Are we back up?
Yeah, it's coming up.
Okay, great.
Yes, acknowledgements.
Okay. Quick acknowledgements. So as Julia already mentioned, this presentation today covers some of the, at a high level, the stuff in the report. There are a few documents associated with the task force work. There is an executive summary, a main report, a summary report, and then we broke out from the main report a Meteorology 101 document, which I think folks in the power system sector who are not meteorologists might find very useful. The main report is rather long, and so for people who are looking for a high level summary, we would recommend the summary report. I'd like to really acknowledge particularly Julia for her hard work pulling together that summary report, along with Karen Matchett, and also a couple of other folks who were really heavily involved. Michael Milligan was helped me with some of the writing, and Priya Sridharan rather did a lot of work providing some initial review. And then there were a number of people who did very deep review, and I'm greatly appreciative. The document is a lot better as a result of that. And I also do want to acknowledge that GridLab provided some additional funding for this work as well. And then just a quick disclaimer, I've tried to keep most of the presentation objective, but there are some things in the presentation that are my own views and not necessarily official views of folks in the task force or their member organizations. When the PDF comes out, it will be clickable and you'll be able to use that to get to the right places. So really quickly, I'm going to go through increasing weather dependence, transdisciplinary disconnects between the power sector and the meteorological sector, the attributes of the data that we need. I want to pay particular attention to validation, which I see as being one of our most critical gaps. What's our current status of data that we have available today, and what are the impacts of the gaps, and then a roadmap to the future. So we'll start with increasing weather dependence. It's the motivation, which is the energy transition, fits very nicely with E6 mission. Our system, as we all know, is changing very radically, and it is full of uncertainty, and we need to evolve our methods. And ESIG has done a lot of work in this area, particularly working with Derek Stenslick of TELUS on the Rethinking Resource Adequacy initiative. And I think this project kind of fell out of some of that work. And the two documents that are out there from ESIG are noted here. So I want to just at a high level talk about the evolving energy and weather nexus. This diagram here basically shows how things are changing between 2022 and converging to 2050 in the middle, showing how weather impact is increasing, that's the blue arrows, and how weather complexity is increasing, that's the red arrows, and then gives you an indication of what's happening on the load side on the left and what's happening on the generation side on the right. So we can see from the load perspective that loads are increasing because we basically need to electrify everything. Transportation loads in particular are increasing, and then commercial and residential loads increase as we increasingly move over to electric heating. And industrial loads as well, as we start making things with more industrial processes. At the same time, we need to get down to basically not using fossil fuels as quickly as possible, contrary to what some people have been saying in the COP conference right now. We do need to phase out fossil fuels, and that will not take us back into the caves. In the meantime, we'll have a massive increase in wind and solar. Personally, I think that there's probably room there for nuclear and hydro as well, but that's typically not what's on the roadmap. That means that we've got a massive increase in weather dependence from a load perspective, and an even bigger increase in weather dependence on the generation side. So that means that meteorology becomes central to everything. We need to decarbonize and electrify almost everything. And right now we have a major gap in the fuel supply knowledge. And that's kind of where I've tried to position myself. This is an old version of myself before I decided that I only have one body and I need to actually take care of myself. The risks are shifting, weather dependence and weather complexity is increasing. And a few years ago, I worked on a paper with Josh Novarchak and some other folks from NREL around the evolving role of extreme weather events in the US. And that was sort of the start of getting really heavily involved in this area. But in spite of all that, and that it's really clear how important weather data is, we're basically flying blind, or at a minimum, our vision's pretty limited. We're doing a very good job on the operational side with forecasting, but we're not doing a good job with respect to understanding the need for really good meteorological data from the perspective of planning. And there is really an imperative for a dedicated, accurate, and expertly curated national, and ideally beyond, really global weather information, and I say information versus data, system to support the energy transition. We don't just need data, we need to know how to use that data in an effective way. And that brings me to another quote by Rory Bremner, who's a Scottish comedian. He says, if you put garbage into a computer, nothing comes out but garbage. But if this garbage, having passed through a very expensive machine, is somehow ennobled and none dare criticize it. And that epitomizes what I feel where we are right now. I think we're doing a huge amount of work with data that we don't understand the flaws of. And that was my motivation for wanting to do this work. And coming up with this report that's on the right-hand side. And it's not just me that's saying this. So I've just pulled together just a subset of reports and presentations that I'm familiar with, and I've highlighted in yellow here some of the things that folks are saying. For instance, there's a major paper by Alexander Kies, where he says in the abstract, these models require, talking about power systems models, these models require accurate data and renewable generation to develop their full potential. Using different data can lead to conflicting results and policy advice. He goes on to say significant differences between these data sets are found, resulting in cost differences of about 10%. These findings indicate that much more attention needs to be paid to large uncertainties in the input data, and I could not agree more. Derek at Talos has noted in several of his presentations how weather is the single most important driver of resource adequacy. And a number of grid lab reports have also noted how important weather synchronized data is to resource adequacy. And they note in one of their fact sheets that regardless of the RA analysis approach, the availability of more high resolution, hourly power system data, as well as information about likely future weather conditions, would greatly improve our understanding of RA challenges. And then there are a number of other papers that are referenced here. And actually, that reminds me, a number of these papers are by Hannah Bloomfield. She was another person who I should absolutely acknowledge. She played a very major role in writing the climate change section of the report. So let's look in a little bit more detail at this weather dependence and get kind of into the weeds. I'm not going to go through this chart too much, but I'm going to show the primary things that are driving weather dependency. On the top here, you've got various phenomena in the atmosphere, clouds, aerosols, precipitation, temperature, humidity, insolation, groundwater, snow, and wind, and how they all interact with one another. And then those interactions result in interactions for solar generation, hydro generation, thermal generation, load, transmission and distribution, and also wind and solar. Basically, we are going into a situation here where, I'm sorry, I unfortunately couldn't use presenter view. But basically, key points that I want to make clear here are that weather is driving the demand, weather is driving the load, the generation, and it's also the major driver of outages, and it's a major driver on the transmission and distribution system. It affects everything. It's central. In a nutshell, there's a lot of complexity. And we've got to manage and mitigate this weather dependency. And one of the things that I've always tried to explain to people in this realm is that there's variability and there's uncertainty. And a lot of people look at forecasting as being the way that we resolve our weather dependency. And the bottom line is that while forecasting is important and is helpful, it only helps you to mitigate uncertainty. You cannot mitigate variability with forecasting. Variability is baked in after you've planned and built the system. You have to mitigate variability on the front end. And that is why planning is so important and why some of the things I'm going to say today are so important. And we're kind of missing the boat on it. Most of that variability and uncertainty in the system becomes due to weather at high renewable energy penetrations and as we transition to more weather-dependent load. And there are a number of ways we can mitigate that variability. We could do it via energy storage and power to gas. We can do it by overbuilding. But neither of those two methods right now, or fossil backup, neither of those methods right now are particularly efficient or cost effective. They may be in the future, in which case I will be out of a job, but for now, they're not the best way to do it. An informed mitigation recognizes that there is a continental scale to weather. It builds transmission and generation accordingly. I am one of the people who will scream from the rooftops that transmission is the most important component of the energy transition, but also placing our generation in a strategic way is really important too. And both require high quality, high resolution meteorological data. And that data is currently inadequate, and that pun is intended. So next, what are our transdisciplinary disconnects? When we do power system modeling in a nutshell here, this is what we have traditionally done. We have a load time series that we normalize, and we have we can create a temperature to load function. And then you, without getting too deep into the weeds on this, you can play a lot of games using Monte Carlo simulations to basically do your resource adequacy type studies and other power system modeling type studies. And the weather dependence was relatively simple in the past, when it was mostly about how temperature affected things. But now we're moving into a world where we have wind and solar generation thrown into this mix. And at first blush, that seems as if it's probably not going to make a huge amount of difference. Why can't we just, we've just got a couple more variables. So one would think that maybe, as long as we've got decent data around those, that we can move forward. But it's actually quite a bit more difficult than that, and I'm hoping that that will become clear through the rest of the presentation here. So the first thing I want to talk about is how modern weather data sets are increasingly complex. In the past, we've used in our sector largely observations of temperature, and they are observations. And typically our data nowadays that we're using for wind and solar are not observations. They're based on observations, but they're not actually observations. And that paradigm shift has kind of snuck up on the sector, and a lot of people don't realize that. And they're using the data as if it is observational. Observational data obviously has some uncertainty associated with the measurement. You have to quality control it. There's a degree of uncertainty to how good the measurement is, but the uncertainty is fairly small and easy to quantify. But the data we're using now is not. And so we need a transdisciplinary approach where the meteorologists are teaching the power sector people about the uncertainties, and similarly, the power sector people are teaching the meteorologists about what they actually need and about how those uncertainties impact the work that they do. It needs to be coordinated, it needs to be well managed, it can't be scattershot, and we need to have a knowledge of all the needs and the capabilities and sources of data and of the modeling that we're doing with the data. And so I'm going to use today's atmospheric river that folks in the US, particularly the Western US, will know is occurring. We have a major weather event unfolding on the West Coast right now as an example of that complexity. So on the right-hand side here is a 36-kilometer resolution model run of the forecast for this atmospheric river. And you can see that there's quite a lot of precipitation going into Washington. Now on the next slide, I'm going to show a close-up of that precipitation, and this is from a 12-kilometer model run. It's exactly the same model from exactly the same modeling center at the University of Washington, where I did my PhD. And you can see that there's quite a lot more structure and complexity at 12 kilometers, even though it's the same model run. If we then look at it at 1.33 kilometers of resolution, you get a completely different picture. We can see now that this is hourly rainfall, actually three hourly rainfall for today. And it's actually for 1 p.m. this morning. And you can see you can see there's an area of very heavy rainfall. Let me see if I can put a pointer on here. Hopefully I can, without taking too much time up. Shoot, that wasn't clever. Oops. Oh, I've really screwed it up. Sorry, folks. Is it still shared, Julia?
It's now showing the title slide.
Yeah. Okay. I'll get back to it. Okay. I'll try and explain it without the pointer. This is why I wanted to get the presentation view. Okay, so you can see in the bottom right of the picture that I really do need a pointer of some sort.
There's an annotation up in the upper right-hand corner.
Upper right?
Yeah. There's a squiggly line where you can use.
Oh, I see it, yeah. Can you see that now?
I don't think you've selected one. Oh yeah, there you go.
Yeah.
Okay, cool. So you can see that area of very heavy rainfall right here. This is 2 inches of rainfall, or about 6 centimeters in a 3-hour period. In an area of higher terrain here, you can see also multiple areas of really high rainfall here. You can see no rain at all in this area right here because it's rain shadowed behind the Olympic Mountains. And these are the types, and this is a very heavy rainfall over Mount Rainier. These are the types of features that we see when we start modeling things at high resolution. One of the things that you need to be aware of here is that this is a simulation. These are not observations. And in exactly the same way, the data that we're using today for power system modeling for wind and solar is synthesized. It's not from observations. We don't have observations in the millions like you're seeing on this output. And that's really important to realize. The thing that I have to remember is to turn the annotation off before I go to the next page, because otherwise it restarts the thing. Okay, so what are some typical sources that are used for the data for power systems modeling? So for load and hydro, typically the data comes from observations. And sometimes it comes from models in order to be more consistent with the wind and solar, or just for general ease. And it's typically very centralized in the load centers or the hydro basins. An entire hydro basin can be considered as one entity. And from a load point of view, our major cities central locations where we need to understand what's going on with the weather, particularly the temperature. But for wind and solar, we have wind and solar plants that are spread out across broad areas, which makes the problem much more difficult. And so wind and solar data typically is not available in the observational form to be able to do this type of analysis. So we have to synthesize it. And that leads to a lot of problems because people grab hold of that data and they're treating it like it's an observation. One could say, well, we have wind and solar farms, so why can't we use their data? I will come back to that in a little bit and explain why. A lot of times it's just not available. It's just not made public. And then the other issue, of course, is that there's no data at all for future project locations. And so a number of different sources can be used, and often they're mixed and matched, and there are problems with that I'll go through later on as well. Basically, the bottom line is that all data is not created equal, and it can be very different even from the same modeling system. So again, another example of the same modeling system for today. This is solar output forecasted for this afternoon, actually for right now, from the University of Washington model. One is at 36-kilometer resolution, which is the equivalent of the ERA 5 data set that some of you may be familiar with in the power systems world. The other one is from the 1.33 kilometer domain, much higher resolution domain, much more compute power needed to produce it. And you can see the structure is entirely different. And to say that that doesn't matter is a really bad move, because as you can see, there are areas where there's some solar radiation in the 1.33 kilometer domain where it's pretty dark in the 36-kilometer domain. And guess where developers tend to put their solar plants? Solar plants get sited where the best resource is, and that's where the terrain tends to drive good resource. So we've got a couple of methods by which we can produce our data for power systems modeling. One is using a bottom-up approach, and the other one is top-down. Bottom-up basically estimates the resource at every renewable energy plant, including future locations, to calculate generation. It requires very accurate high-resolution data that simply isn't available in the observational form. It works even where there's no generation history, but the problem is that you don't know whether the data is any good because there's nothing to check it against. Top-down method basically estimates the generation based on a relationship that's developed between a generation history and a coincident weather record. And the accuracy of the weather record becomes less critical at that point. But it needs to be consistent, and it requires a generation history. And that's the method that's typically used for operational forecasting. But no matter which method we use, we need to be able to estimate the renewable generation at an appropriate aggregation level for the same pattern that is driving the load, and we need to do it chronologically, because if the load is being driven by a weather event that creates low temperatures or high temperatures, and that same weather event affects your renewable generation, then those two things both feed into adequacy. So this slide's a little busy, but the idea is to basically show that, as I mentioned already, for temperature at our large load centers, we can basically use observations. Even though there's still a lot of structure in our temperature field, we don't actually need to know the temperature across an entire region. But for wind and for solar, we do need to know the details of wherever we're tending to put our wind and our solar. And it can vary by a dramatic amount in a matter of a few miles. So just kind of going off the text here, power system models have always incorporated weather data, but the treatment has typically been concerned with temperature and its impact on load, and then the sampling of hydro years. So it's come from urban areas and existing streamflow measurements. But for wind and for solar, as I've mentioned, that data is not widely available and it must be synthesized. The fields vary very rapidly across short distances. The data is sparse, it has a short history, and where it does exist, it's mostly proprietary. And so what I want to bring you back to is that quote that we had from Rory Bremner, garbage in equals garbage out. And there's a lot of garbage out there, and that's something I want you guys to know. Okay, so what are the attributes of data that we need? Now we've kind of covered the transdisciplinary disconnects. I've tried to categorize these into three different broad categories. There's physical requirements, relevancy requirements, and usability requirements. I'm going to go through each one, and I'm going to see how much time I've got. I'm going to have to go fairly quickly, but I want to spend a few minutes on this slide. The data needs to be representative of the actual weather, and it needs to be coincident, physically consistent, and of all of the required weather variables. So in other words, what I'm trying to say by that is, so right now we have this atmospheric river event occurring on the West Coast, for instance. That is bringing a huge amount of rainfall into the Northwest. It's actually also bringing some very strong winds at our wind farms in the Northwest. Some of the wind farms, and I'm going to show you that in a moment to kind of bring this point home. At the same time, it's bringing in very, very warm air, and so our loads are low. So that, in this particular instance, makes adequacy, not really a big issue because we don't have much load. Now, what if we flip that around though? We had a situation where the very same weather that brought my really high loads to cities in a particular area also brought a period of no wind and poor solar. Then we could have an adequacy problem, and that's why it needs to be coincident and physically consistent and representative of the actual weather. And I'll show you what I mean by representative in a moment too. It needs to have sufficient resolution, and I'm going to hit really hard on that one, so I'll skip over it for now. And it needs to be chronological. The reason it needs to be chronological is what happens this hour now affects the next hour and the hour after that. The reason being is, it's always had an effect on load, but the reason why that's now really important is because it impacts storage. So if I've got a period of really good solar resource, that occurs before a particularly warm afternoon, then I can be charging my storage. But if that period of if that period is one where my solar and my wind is poor, and then I've got a period of high load immediately after, then that could create an adequacy issue. It needs to cover multiple decades with a consistent method, because believe it or not, even though all the talk right now is about climate change, climate variability is a big deal. In the 1980s, we had some extremely cold weather across the United States, and people have short memories. It doesn't mean that it's never going to happen again. Variability is baked into the climate system. It's a naturally occurring phenomenon. It needs to be validated and the uncertainty quantified. Right now, that has been done really poorly in almost all of the data sets. People are reaching out to data sets like ERA 5 and saying, oh, this is really great. I can go out to the website on Copernicus and download the last 50 years worth of data, and I'm off to the races. But what they don't realize is that in 1950, we didn't have any satellites going around the planet. And so the uncertainty of the data from the 1950s is much higher than the uncertainty of the data today. It has been validated, but has it been validated from the perspective of how well it predicts the wind output at a location of a wind farm that's sat in topography? Has it been validated on a day when it's particularly cold and there's a resource adequacy issue and also an inversion that's changing the surface weather so that it's foggy, so my solar is different, or so that the wind isn't mixing down from aloft? Unfortunately not. It needs to be periodically refreshed to make sure that we're using the state of the science. So one of the data sets in the US that we're using right now a lot is the Wind Toolkit. It's a great data set. It's also 10 years old. We need to redo it. And it needs to be regularly extended. And I could say the same thing about the Wind Toolkit there, and we'll go on to those things in a moment in a little bit more detail. And then the stuff in the green, the usability requirements, are the things that I think we're really missing and that we really need to focus on. We really need to be able to have this feedback loop across the sectors. So it needs to be expertly curated so that people know how to use it, and not only so that the folks who are users know how to use it, but so that the people who are producing it know how to produce what's needed. It needs to be publicly available and easily accessible. But at the same time, one of the things that I like to tell people is that right now I feel like we're just throwing data onto the internet, and just it's like handing a permit driver the keys to a Formula One racing car. People don't have a good feel for what the uncertainty and the problems of these data sets is. And then it needs to be transparently documented, which comes into that. So I'm going to hit on these two physical requirements and the validated and uncertainty quantified requirement. And then we'll continuously sort of talk about expertly curated. I'd love to go through all of them in a lot more detail than the report does. This is just that same slide as the last one, only using a table. And this is for folks who don't get to see the webinar, so they can look at it offline. So looking at physical requirements again, I'm going to use an example from, hoping I can get rid of this. Yeah, there we go. I'm going to use an example from today. So this is actually a loop of the next 48 hours of wind. It was initialized last night at 4 p.m. Pacific time. And it's a two-day forecast of the wind speed in the Columbia Gorge, where there is a lot of wind energy currently located. And again, I'll try and annotate a little bit. There's a huge amount of wind up in this area. There's a lot of wind down in this area, and there's quite a lot across here, and there's a bunch of wind farms in this area as well. And then there's actually quite a few up here too. There's about 5 gigawatts of wind in this area. This is where I did my PhD studies, is on wind in the Columbia Gorge. And my advisor was always fond of telling me that the Columbia Gorge is like a laboratory to the world. And it's a great way to look at the way that we can model mesoscale, small scale phenomena using numerical weather prediction, and also look at what some of the difficulty and uncertainty associated with that is. But not just for that region, these same issues apply across all of numerical weather prediction. So I've got some questions here that I'm going to pose as we step through it. So you'll see that these fields look fairly smooth right now at 4 o'clock. That's because this is initialized from the global forecasting system model, which is a lower resolution model. And I'm going to step 1 hour, if I can turn off my annotation. Oops, I knew that was going to happen. Let's try again. Well, okay, so I've gone, let's try one more time. I was really hoping to be able to bring up presentation view. Okay, so I managed to just step at 2 hours there. So all of a sudden, we've got all this structure. So what's happened? Did the weather suddenly change? No, that's not what happened. What happened is the numerical weather prediction model synthesized these fields. It basically created the weather that it thinks is happening at higher resolution because the original field didn't know about all the topography in this area, and this model does. And this is how we synthesize weather data. So when you're using the wind toolkit, you're not using observations, you're using data that's been synthesized by a model using this methodology. Now, obviously, we don't have observations at every single one of these locations to see whether or not this data is correct. But what you can see here is a huge amount of structure. And if we go back to this annotation, to our annotations again, remember there's a bunch of wind farms down here, and there's no wind. And there's also a bunch up here, and there's tons of wind. This distance here is about 10 miles. So vast differences. And also look up in this area as we go through the loop. I'm going to step the loop forward now. Turn off the annotation. So it'll go. So this is the next 48 hours. So you can see it's a pretty windy period, but not much wind down at those wind farms near the river. And then all of a sudden, you'll see a bunch of wind comes in at the end for the last 2 hours. See if I can step through that again. So do you see how that wind is encroaching on the river through the loop initially? I'll let it go through twice this time. So the wind gradually moves towards the river, and then all of a sudden it fills in. And I know that that might seem like a minor detail, but it's really important from an adequacy point of view. What's going on is that there's a front going through, and that, if you look at the period right here, the wind is kind of coming from the east. This area here is currently stuck under an area of relatively cool air. We had some really cold air last week, and it hasn't all scoured out yet. And so this super warm air from the atmospheric river is going over the top. And that's preventing the momentum from getting down to some of these wind farms that are closer to the river. But meantime, the wind farms further away from the river are getting a ton of wind. Now, what if the model sometimes gets that transition wrong? Well, the answer is that it does, and it does fairly frequently, and not just in the Columbia Gorge. It gets it wrong in a lot of places a lot of the time. And that could pose a really major resource adequacy risk. And so I'm hoping that it's becoming clear to people how right now we're using a ton of data and we're making these policy decisions using data that we haven't validated. But wait a minute, don't we produce this data and use it for operations all the time? Well, we do, but the difference is when we're using it for operations, we actually have the operational weather data, and that's used by the forecast vendors to tune the forecasts. When we use it for the purpose of, when we use numerical weather prediction for the purposes of doing power system modeling, we're typically using lower resolution data, and we haven't validated it. So that brings me nicely to validation, the most critical gap. So in a study I did with Grid Lab, let me check the time. In a study I did for, I should speed up a little bit. For Grid Lab, I actually looked at the skill of the model for periods where there were adequacy risks. And what I found was that in summertime, the model tended to underpredict the wind generation. In the wintertime, it tends to overpredict it on a regular basis. And when we have tail events where the load was high and the resource was low, was when the model tended to overpredict it the most. And hopefully folks can see what a big issue that is. And again, while it isn't an area that I have a lot of knowledge of, I know that this is a problem in other places too. And other people have done studies in Texas where data is now becoming more broadly available that have shown that this is also a big problem. So what we need is comprehensive industry-wide data transparency and sharing. We need to share the meteorological data, the generation data, and the availability data. There's little proprietary value to this data, even though folks won't share it, but there's tremendous untapped value if it's made public across all generators, because we can validate these synthetic data sets with it, and also we can use it to improve the initialization of the model, which will improve the data coming out of the model. And ERCOT's really leading the way on this, and others need to follow as soon as possible. And that might require legislation. I would prefer it if we could nudge people to do it, but ultimately it is imperative that we get this done as quickly as possible. So what's the current status, gaps and impacts of that? So right now, the data that's available today falls into a few categories that are broadly used. There's the ERA 5 data, which is a phenomenal data set in that it spans a very long period of time, but it's what's called reanalysis data. So it's not actually observations, it's based on observations. So the observations are put into a numerical weather prediction model, which will then fill in the gaps. And then there's another data set called MERA 2, which is similar to ERA 5, but I would recommend using ERA 5. It is considerably superior. But ERA 5 does not have sufficient resolution to be able to be used for doing wind and solar estimates. Yet it is, and there's a lot of policy decisions being made based on it. And then there's the NREL data, which is the wind toolkit, which is a much, much better data set, much higher resolution. Problem is that it's only really represents 2007 through 2014. It is being extended, but it's being done in a very ad hoc way without really a plan. And what we really need is we need a data set that's as good as the wind toolkit, that is extended on an ongoing basis. And as we'll come to in a minute, that's not difficult to do. Another model that people have suggested using and that some folks do use for weather data is the high resolution rapid refresh model. It's a tremendous model, but it's a forecasting model. And what that means is that it's not actually designed for producing the type of reanalysis data that ERA 5 does. It's basically designed to produce a forecast as quickly as possible on an operational time cycle. And that means, and also the most accurate forecast on an ongoing basis as modeling improves. So it's a moving target. The model is constantly being improved, so the biases in the model are changing all the time. So that's not a great choice either because of that reason. And you can find a lot more details about this in the report. And because I don't have much time, I'm going to skip through this one. This one was provided for general offline reading anyway. I wanted to make a quick word about climate change. I know I haven't mentioned it all, and a lot of mentioned it here, and a lot of you are probably wondering why. And the reason is that I feel that we really need to get the house in order with respect to climate variability. That's our #1 priority. And by doing that in an ongoing fashion and having these ongoing continuously extended data sets that are high quality, we'll be able to get our arms around some of the trends that are already happening. We also can begin to validate and quantify the uncertainty of climate change models. If I give you a bunch of data that tells you what your wind looks like in 2030, you never know whether it has any value at all. For all you know, it could be complete garbage. And we'll never know until 2030. So therefore, while the need is large, I believe the impact of climate change is of second order compared with the increased risk of increased weather dependency and the need to properly quantify climate variability. This is a table from the paper that I put in for people who want to read it offline later. And those are the footnotes. So let's look at a roadmap to the future. First of all, as I mentioned, we need this behavioral change and transdisciplinary coordination. I've thrown this plot in on purpose. It's a loop from the work I did while I was at Iberdrola back in the late 2000s. You can see all the structure in the wind field here. The exact same forecast, or data rather, from ERA 5 is shown on the right-hand side. There's no structure at all there. That's the data that's being used by a lot of people today. Point being there is we need to stop assuming we understand each other's specialities and start working more closely to meet each other's needs. It's a recipe for disaster to just download data off the internet and use it. Garbage in, garbage out. So we have a number of different routes we can go to get to this. It's not easy, but it is possible. And we can use a reanalysis plus an observation plus a machine learning approach. My gut tells me that that might not be sufficient because the problem with machine learning, while it can do a really good job, is it tends to not do a great job with the outliers, and the outliers are the things that matter. We could use moderate resolution numerical weather prediction with this system called GAN downscaling, which I don't have time to go into today. It looks very promising, but requires a lot of validation. Or we can go the old-fashioned route, which was what we did for the wind toolkit of high-resolution numerical weather prediction. It will definitely work. It won't be perfect, but that's part of the process, is helping people understand where the imperfections are. How much will it all cost and how long will it take? You know, we're talking millions of dollars here, tens of millions, but we're looking at investing trillions of dollars in the energy transition. So it's a fraction of a percentage point. And it is just it's so a no-brainer in my mind to do this. We're going to be spending money to save money in the long term, because right now we really are flying blind. And so I'm going to leave you with some quick thoughts about how we move this forward. I'm not going to go through this particular chart. I put it in there for folks who are on this webinar and who see this webinar later, who this resonates with and say, hey, we need to do something about this, because we do. And I would love to discuss this in more detail with those people. And so I will leave it at that and go back to a picture of the report. And I hope this was informative, and I'd be happy to take some questions.
Thanks so much, Justin. Such a whirlwind into the report. I recommend everybody go to the webpage and read the report in either shorter form or the complete report. We have time for a few questions. I'll start with, I think it's more of a comment than a question, but Justin, maybe if you care to comment. Why are power system models generally done in random outage? Why are power system modelers, I think, generally done with random outage draws, Monte Carlo, when there is a clear correlated failure modes, primarily based on weather conditions?
I think a lot of that is historical. Some of the power systems modelers on the call would probably be able to answer it better than me, but my understanding of it is that, you know, the understanding that there is a clear a clear correlation between weather and outages is, while it's sort of obvious to you and I, Julia, I think it's only really become common knowledge in the last decade or so. I think that most really good resource adequacy shops are starting to move over to using non-random outage draws for power system modeling, but it's a good comment.
Thank you, Justin, and I fully agree. On slide 18, the question is, are there any advances on numeric weather prediction that attempt to adaptively refine the spatial resolution? It means adaptive mesh refinement approaches.
Yes, there are, and the report goes into those in some detail, and this is where that the adversarial network methodology, which is a form of AI, could be very useful. If you are able to produce the model at moderate resolution and then have maybe a year or 2 years of high resolution numerical weather prediction, then you can potentially use non-numerical weather prediction methods that are a lot less computationally intensive to be able to downscale to 1 kilometer, say, from 5 kilometers, with a lot less computational requirement. And I think that is probably the methodology that we're going to end up using as we move this process forward. And there's some really interesting work going on in that area. I could spend another 30 minutes on it, though.
And that leads nicely into the next question, which is, what is your take on AI systems like GraphCast from Google DeepMind? Would they become an essential tool for data reanalysis / synthesis for power systems?
That's a great question. My hope is yes. I think they have tremendous potential. GraphCast is now beating numerical weather prediction most of the time. The problem for our area that we're in right now is, when does it fail? And it's only as good as the underlying data. And so where there are failure modes for numerical weather prediction, those same failure modes are going to happen for the downscaling methods because the training data is wrong. And so there's always going to be a need to keep on pushing forward the quality of the fundamental underlying science behind weather prediction, in my mind. Somebody could try and convince me otherwise of that, but right now that's where I'm at, and I'm concerned that if we don't do some really dedicated validation, we could end up in a scenario where we fool ourselves into thinking we've fixed the problem, and then it rears its ugly head in situations where we have adequacy issues. And again, that's a question. It's a great question. It's something I'd love to sit down with the questioner and have a beer and spend some more time on.
Right. Thank you. I'll take a couple of more questions, though we're on top of the hour. Let it run for maybe 5 minutes over. The next question is, are solar forecasts facing a similar level of inaccuracy as the wind example you were showing?
Well, so first of all, I want to make the distinction between forecasts and synthetic data sets. So the methodology that's used to produce synthetic data sets is generally the same as the methodology that's used for operational forecasting. Operational forecasting, as I showed in one of the slides, I think it's, well, yes, it is. It's this one right here. Our operational forecasts are actually better than our historical data that's been used for planning, which is a terrible state of affairs. And The primary problem is that we don't have data for validation. And as we're building out the renewable energy system, I know that I'm kind of going off at a tangent to the question, but what's really important is actually getting the data and doing the validation at the level that we need to make sure that we're placing our synthetic data into the context of where it's needed. So for instance, are we able to synthesize data for periods where there are high loads and low wind, or high loads and low solar? But to answer the question, yes, both the forecasting of solar and the production of synthetic data sets is difficult. It's not as challenging for wind as it is for solar. There's two reasons for that. One is that wind is a cubic relationship with the wind speed, the wind power, and so any errors are magnified because of that. And the other one is that the overall variability of the solar field is slightly less than it is for the wind field, because the biggest impacts on solar are clouds and aerosols, versus for wind, there's a lot more atmospheric effects that are occurring near the ground, where topography can make a much bigger difference. Now, of course, topography does force clouds as well. So the short answer to the question, and this is dealt with in the report, but you know, I could talk for 10 minutes on this at least, is that solar is a little bit easier. The solar data sets are a little bit better. And also the other thing with solar is we have satellite observations of solar, which provide us with a way to remotely sense over large areas. We don't really have that ability with wind. We do more so over the oceans, where you can use scatterometer data to get an idea of the wind speeds over the oceans using capillary waves. But in a nutshell, yes, the same problems exist. They're not quite as bad for solar as they are for wind.
And Justin, since you started talking about forecasts, I'll maybe jump a little bit and off the order of questions here. But Russ is asking, can synthetic high resolution data in short-term forecasts be accurate? And if so, is it effective method of filling in missing spatial and temporal data?
Could you read the question again? I missed a couple of words.
Can synthetic high-resolution data in short-term forecasts be accurate? And if so, isn't it an effective method of filling in missing spatial and temporal data?
Right. Well, so I think I'm going to try and reframe it slightly. I think what Russ is saying is correct, that high resolution synthetic data can fill in the gaps, and those are, I mean, they're essentially hindcasts if we're looking in the planning sense. And I'm assuming that what Russ is talking about is using high resolution synthetic data for planning models. It can be a useful way to fill it in. The thing is that we don't have good knowledge of how useful it is and where it fails. And the work that I've done suggests that where it fails is where it matters the most. So in other words, for instance, if, and that was why I showed you that example of today, the wind in the Columbia Gorge. That's a common failure mode. I'm not saying it's wrong today. It's probably reasonably good. But one of the common failure modes for numerical weather prediction is when you have a strong inversion near the surface. The models tend to mix that inversion out too quickly. And so you end up with warm air coming down to the surface that has high momentum, strong winds. You also mix out the fog and the clouds. And so those two things together provide you with more wind resource than actually happens in reality, and more solar resource than happens in reality, because you scour out the fog and you bring down the wind. Those two things tend to happen at the same time. That forecast, if in operations, forecasts are incorrect for load because the temperature is under forecasted, is over forecasted to be too warm, and so loads are higher than you would expect. So in other words, when I have adequacy issues, my operational forecasts are wrong, and also my planning forecasts are wrong. It's a double whammy, and basically a lot of the conclusions that we're drawing right now about whether or not we can do things with renewables, they might be wrong. I'm not saying the sky is falling down. I'm saying we need to check.
All right, I'll ask the last one. I think it's sort of related to the previous, you might have deviated into that a little bit already. How much additional real precision versus false precision is added by additional resolution given the uncertainty of that is inherent in input boundary conditions?
I think that's the best way I can answer that question. That's the point. And so that's why I'm really hammering on this point of the first thing we need to do is figure out how good is our data, and we need to do a comprehensive we need a comprehensive project and policy push to get data from renewable energy sources. We are building out this phenomenal network of wind and solar observations, and we don't have access to it. And so, and at the same time, we know that we have to synthesize this data for power systems modeling. It is time that we got hold of that data and figured out how well we're doing and started to improve things.
Yeah, and I think that's the great place to wrap up. So Justin, I would like to thank you once again for this really informative presentation, and the audience for your attention and great questions. As I mentioned earlier, an email will go out once the video file has been posted, and we will answer the questions that we didn't get to. We'll answer them offline and send you the link as well. The next ESIG webinar is on inverter-based resource modeling through the life cycle of a project, reliability perspectives, which will be held next week on December 13th. And will feature Ryan Quint from North American Reliability Corporation. Further information of all of our webinars and meetings can be found on our website at esig.energy. Under events, and our newsletters and informational emails that go out to you, and you are all invited to attend. Justin, thank you once again, and everybody for your interest, and we look forward to seeing you again in the near future. And in the meantime, everybody take care, stay safe, and thanks for your participation. See you soon.
Thanks, Julia, and thanks for the opportunity.